This is very important theorem. Let f be an integrable function on closed interval ab, and suppose fx equal to fa plus integration from a to x on ft dt. Then we have to show that f dash x is equal to fx for almost all x in closed interval ab. Now what is this small f? It is integrable function on closed interval ab. So without loss of generality, we take this f to be greater than equal to 0. We assume this f to be greater than equal to 0. And for this f, we also have to define the function f and x in terms of this f, right? Okay. Let's move on to the proof. So without loss of generality, as f is integrable on closed interval ab, we may assume f to be greater than equal to 0. And let's define the function f and x. That will be equal to fx if f of x is less than equal to n, and will be equal to n if f of x is strictly greater than n. In the first case, if f of x is less than equal to n, then f and x is taking the value fx, right? So the maximum value of f and x can achieve in this case is exactly n, because this fx is less than equal to n. So the maximum value it can achieve is exactly n, right? In the second case, if f of x is strictly greater than n, then f and x is taking the constant value, right? It is taking the constant value n. So for fx greater than n, f and x is again exactly taking the value n. So in both the cases, we can say that f and x is less than equal to n, which means this f and x is bounded above by n. So when defining the function f and x to be equal to this, we say that then fn is bounded. It is bounded above by n. But if this function is having the lower bound, then we say that this fn is bounded. And because f is greater than equal to 0 and f and x can take the value either fx or n. So naturally f is greater than equal to fn. So we can write that the difference of f and fn is greater than equal to 0. Reason: fn is equal to f, or f is strictly greater than n, which is the value of fn. Now we are interested in defining g and x to be equal to the integration of this f minus fn from a to x, because we have given that this f of x is equal to fa plus the integration from a to x ft dt. That is why we have defined the function g and x to be the difference of this from a to x. We need these limits. So this is further equal to the integration from a to x of f minus the integration of fn from a to x. This is your g and x. So what is integration from a to x of f? That will be equal to g and x plus the integration from a to x of fn. Let's mark this as 1. Now since the difference of f and fn is greater than equal to 0, so therefore because this difference is positive, we say that g and x is an increasing function, yes. So therefore we write that g and x is an increasing function. And because g and x is an increasing function, we say that its derivative is then greater than equal to 0, because g and x is an increasing function. It is given that fx is equal to this right hand side. Let's make use of this now. Since f of x is equal to f of a plus the integration from a to x on f t dt. Right? So this is further equal to f of a. And what is the integration from a to x f t dt? From 1 we are saying that the integration of f is equal to gnx plus the integration of fn. So writing here it is equal to gnx plus the integration of fn. Let me write fn t dt from a to x. Let's derivate both the sides. F dash x is equal to the derivative of fa because it is your constant function, so this derivative is 0, plus gn dash x plus the derivative with respect to x of the integration from a to x, this fn. Now this gn dash x is greater than equal to 0, so we are getting the inequality. This gn dash x is greater than equal to 0. When derivating this integration, we get fn x almost everywhere. So we have got that f dash x is greater than equal to fn x almost everywhere. Right? Now this n is arbitrary. Arbitrary means n can take any value, and for any specific value of n. We have defined the function to be this fn x. So let me consider the specific value of n for which fx is less than equal to n. We are getting the value of fn x to be fx. So from here we are writing that because this n is arbitrary, since n is arbitrary, so the left hand side, that is f dash x, is greater than equal to, for fn x I write fx. Almost everywhere. I hope this step is very clear. So consequently, the integration of this on both the sides from a to b. So this is greater than equal to the integration of fx from a to b. This is dx. This is also dx. By fundamental theorem of calculus, this integration is equal to f of b minus f of a. So this implies we are getting the integration of f dash x to be greater than equal to f of b minus f of a. By hypothesis, please mark this as 2. Fundamental theorem of calculus says that, fundamental theorem of calculus states that if this f dash x is continuous on closed interval ab, then we get the equality sign over here. Also from some non-standard conditions about this function, where because like in this Lebesgue integration, the function is not Riemann integrable, right? So for some non-standard condition we write this integration is also less than equal to fb minus fa. We are getting both the inequality signs, right? Please mark this as 2 and this to be as 3. So from 2 and 3 we get the sign of equality. So from 2 and 3 we get the integration of f dash x from a to be equal to f of b minus f of a. And from the theorem of fundamental calculus, this is equal to the integration from a to b f of x dx. From here, we have used this integration to be equal to fb minus fa by the second theorem of fundamental of calculus. So this implies the integration from a to b f dash x minus, taking this integral to the other side, so we get the difference of f dash x and fx to be equal to 0. And since now this integrand is also greater than equal to 0, from here, from this part we have written f dash x is greater than equal to fx, that is f dash x minus f of x is greater than equal to 0, right? So as this integrand is greater than equal to 0, and also we are getting this integration to be equal to 0. Let me write this. Since f dash x minus f of x is greater than equal to 0 and this integration is also equal to 0, so from these two we say that this f dash x minus f of x is equal to 0 almost everywhere. This is what it implies. So hence from here we say that f dash x is equal to f of x almost everywhere. Hence we have shown that f dash x is equal to fx almost everywhere for this function f, which is integrable on closed interval ab with the given condition. Okay, thank you.